Welcome back, JQ Adams family. Ankh here. Today, we're going to be doing problem number 6-7. Oh my god. Okay. Hello, JQ Adams family. Ankh here. Today, we're going to be doing problem number 6-7, a Gauss's law problem. And what we're going to be doing is finding the electric field at different radiuses in the experimental setup. Now, what we have here is an apparatus of a solid conductive sphere surrounded by a solid 1 centimeter thick shell. A right now is asking for us to find the electric field at a radius of 1 centimeter, which is great for us because one thing we know is that our sphere is solid and has a radius of 2 centimeters. Because it has a radius of 2 centimeters, that means our radius that we're trying to find is only halfway of the radius of the sphere. Now, we can know one thing, and one thing only, because we only need to know that it's a conductor. And because it's a conductor, we can assume that it's in electrostatic equilibrium. Now, if you want to get technical, a conductor is said to be in electrostatic equilibrium when charges are at rest and no net motion of charge occurs anywhere inside or on its surface. Now, this has a constant charge of positive 8 microcoulombs that is never changing and is always staying inside, evenly distributed throughout this solid sphere. This sphere can be made up of anything: lead, chrome, iodine, anything conductive really. And it really doesn't matter because since we know it's a conductor and since we know it's at electrostatic equilibrium, we can say that the electric field is equal to 0 newtons per coulomb. What? I know, it's crazy. Super easy, right? That's A. Done. Easy. I can't find my eraser. Next, we're going on to B. B is asking for us to find the radius at 3 centimeters. Now, radius at 3 centimeters, we know that it's greater than the radius of our sphere, and it's in between our sphere and our shell. So what does that mean? That means we have to use our electric field sphere equation. And we do that by plugging in numbers. The only thing we really need to know is Q. Q is the charge on the inside. And for us, that charge is going to be 8 microcoulombs because it's inside the sphere and nothing is imposing the electric vectors that are pushing out on the inside. These are all vectors, but they're pushing outside like this. So unless if we're finding a radius that's outside of the shell, we don't have to worry about this charge of the shell or anything like that. So what we can do is finally just plug everything into the equation. So E equals to, turn everything to SI units, please, times 10 to the minus 6 coulombs divided by 4 pi r squared. What's our R? Our R is 3 centimeters. Turn that to meters. 0.03 meters times epsilon naught. Epsilon naught is a constant that we can find in our reference. You plug those numbers into your calculator, you should get 7.99 times 10 to the, times 10 to the 7. Good. Great. If you didn't get that, you're not following along correctly. Or you got your epsilon wrong. Because that's like the only source of error, unless if you didn't copy anything, right? Next, we're going to do C. What? Oh my gosh. I love C. You know why? Because it's asking for when the radius is at 4.5 centimeters. What? 4.5 centimeters? But Marcus, that's going beyond our sphere and beyond the distance between our sphere and our shell. That actually goes in between our shell. So what makes it so great? It makes it great because if you look at it on a microscopic level and you examine only the charges, you'll note that the shell has negative charges all around, evenly distributed, right? And now this inner sphere with a positive charge is going to impose positive charges equally distributed all around the shell. So it's going to look something like this. Boom, boom, boom. And what's going to happen? They're all going to cancel out. That's going to result in an electric field of 0 newtons per coulomb. That's the best part about C. D is asking us to find the electric field at 7 centimeters from the center. If we look at this diagram here, 7 centimeters from the center is approximately 2 centimeters on the outside of the shell. Now, we know we're just going to plug our numbers into E, the electric field equation for a sphere. But the one thing we don't know is Q. Now, how do we find Q? Q is just going to be the addition of both charges, inner and outer. So we're going to call this delta Q for ease, and it's going to be Q inner plus Q outer. Now, in our case, delta Q is going to be equal to Q inner, which is 8 microcoulombs, plus Q outer, which is negative 4 microcoulombs. Negative 4 microcoulombs. Now you just add them to 8 minus 4, which then just turns into 4 microcoulombs. So our Q, delta Q in this case, which we're going to represent and plug into our equation for the electric field of a sphere, is 4 microcoulombs. Remember, put it in coulombs, SI units, everything cancels out, everything turns out nicely. So what do we do now? We remember this. I put it here for future reference, and we're going to plug into our equation. So E equals 4 times 10 to the minus 6 coulombs divided by 4 pi times 0.07 squared epsilon naught. This should give you an answer of 7.34 times 10 to the 6 newtons per coulomb. Now, email me if you have any questions at all. Thank you. Bye. This was it. Done.